Hello everyone, welcome to the new reinforcement learning submodule. This is taught in 10 lectures in the Deep Learning and Reinforcement Learning module taught at Durham. So you may be asking yourself at this point, what is reinforcement learning? Well, in contrast to say deep learning or other areas of machine learning, in reinforcement learning usually we have a dynamic environment. So the environment itself is changing just like in the real world, how our data is always changing around us. And we have these little agents which explore this environment and they move around in this environment. You can think of them like robots or pieces of code which are able to receive some inputs from the environment. And the goal really in reinforcement learning is to teach them how to learn policies to behave optimally within the environment so that they can plan their way through the environment, navigate through the environment, and actually end up learning to control or have some agency over the environment so they can take actions which implicate what happens in the environment itself. And then they can actually learn to exploit the environment by choosing their actions wisely, by learning behaviors and policies which result in them gaining and maximizing reward in the future. So it's a very interesting, exciting field. And the way it's going to work is that we're going to have 10 lectures on this, and the lectures are kind of going to build up and layer from the foundational topics, adding more and more functionality as we go through. The submodule is going to be 100% assessed by the coursework. Maybe you've already had a chance to look at the coursework. So in the coursework, you have to basically train an agent to play a classic Atari game called Gravatar. And Gravatar is quite a challenging game. It's one of the most notoriously difficult Atari games, where you have this little spaceship that flies around and you have to shoot down enemies and conserve your fuel and pick up new fuel. But some of the really difficult mechanics in it are the fact the controls are based on gravity. You're always being sucked into the nearest planet and you have to fight against that gravity. And another really difficult area and problem with the game is that you have to fly to these different planets, and every time you fly to a different planet, suddenly you're shoved into a new environment and you have to work out what to do in this new environment, or the terrain is different. So training agents to behave optimally in this environment is challenging. You've got all of these different mechanics and suddenly you have this new environment, you have to figure out what to do. So hopefully as you go through these lectures you'll gain some ideas about how you can better explore and exploit the environment, training them with different ways. So with reinforcement learning, there is some connection to deep learning, but a lot of the early approaches that we'll be covering don't actually require deep learning. They can just be used directly to optimize. But later you'll see that we'll need more powerful models to approximate various components within reinforcement learning. And that's when you can start to sort of bridge what the content you're learning in the deep learning courses with this content here in reinforcement learning. All right, so this first lecture is going to be a very gentle introduction to the field, to the topic. And we're going to just start with some simple definitions. What is reinforcement learning? What's the definition of it? Who are the kind of key people? What kind of background reading we can do, and how can we compare it to other areas and ideas? Then we're going to go through a very, very brief history of just sort of the key algorithms which were introduced, and this gives us a bit of hindsight and foresight as we look to where the field's going and what some of the major advances have been. And then we're just going to walk through the sort of key components that are required in this field, some of the main terminology you'll encounter in pretty much any reinforcement learning paper, and we're just going to walk our way through these. And then in following lectures you'll have a much richer and deeper understanding of these concepts. Okay, so let's start off with a definition. So this is from Richard Sutton and Andrew Barto. Excuse me. And you can click the reference here and it will take you to the bottom where you can actually read the book. It's also in the reading list. This is really kind of the foundational main book for this topic. And if you look at the authors, Sutton and Barto, many of the major advances in the field have come out either directly or indirectly from their lab. So I strongly recommend that you work your way through this book or chapters of this book as referenced from the lectures. And the course itself is heavily going to be based on their book, just because of how influential their group has been and the way they structure the learning of reinforcement learning is exemplary. So also the submodule will heavily use examples and structure from the David Silver lectures. These are a very famous lecture series. They're a little bit longer than this lecture series. Typically David Silver teaches in about 2 hours per lecture. So there'll be a lot of similarity between the two. So if you do want richer understanding, go ahead and watch some of his lectures on YouTube. He generally goes into a little bit more detail that we don't necessarily have the same amount of time for. David Silver was actually Sutton's PhD student, and now he's the research lead at DeepMind, where he leads the AlphaGo team. You've probably heard of AlphaGo in the news, but also AlphaStar, which is where these are kind of state-of-the-art reinforcement learning agents playing the computer games like StarCraft competitively, entering tournaments and so on. So I'm closely following the structure that they've kind of paved the way for. I think if I was to try and deviate too much from this, I would be actually cheating you just for the sake of it. So, but I will be condensing some of the material and bridging it to the recent OpenAI Gym environment. So OpenAI Gym is a new standard for benchmarking progress in this field, and it's a very useful tool to quickly run lots of different environments and test your algorithms across an entire suite of benchmarks. So let's just read this definition from Sutton and Barto. So they say that reinforcement learning is a computational approach to understanding and automating goal-directed learning and decision-making. It is distinguished from other computational approaches by its emphasis on learning by an agent from direct interaction with its environment without requiring exemplary supervision or complete models of the environment. So the idea is that the agent itself learns to interact with the environment, and you don't need to tell it or give it immediate feedback of what's going on. It has to sort of figure out its policies without giving it all of the rules in the environment. It has to explore it and figure it out by itself. So let's just have a look at some examples of reinforcement learning. So you can click through these videos and see more complete versions by yourself if you're interested. But I'm just going to sort of show some highlights here. Right. So let's start with this one here. So
between 2013 and 2015, DeepMind worked on an incredible learning algorithm by the name deep reinforcement learning. This technique looked at the pixels of the game, was given a controller, and played much like a human would, with the exception that it learned to play some Atari games on a superhuman level. I have tried to train it a few years ago and would like to invite you for a marvelous journey to see what happened. When it starts learning to play an old game, Atari Breakout, at first the algorithm loses all of its lives without any signs of intelligent action. If we wait a bit, it becomes better at playing the game, roughly matching the skill level of an adept player. But here's the catch. If we wait for longer, we get something absolutely spectacular. Over time, it learns to play like a pro and finds out that the best way to win the game is digging a tunnel through the bricks and hit them from behind. This technique is a...
So you can just see at the beginning it's kind of exploring around, and then later it's learning to exploit this environment.
Combination of a neural network that processes the visual data that we see on the screen and a reinforcement learner that comes up with the gameplay related decisions. This is an amazing algorithm, a true breakthrough in AI research. However, it had its own issues. For instance, it did not do well on Montezuma's Revenge or Pitfall because these games require more long-term planning. Believe it or not, the solution in a follow-up work was to infuse these agents with a very human-like property, curiosity. That agent was able to do much, much better at these games and then got addicted to the TV. But that's a different story. Note that this has been remedied since. And believe it or not, as impossible as it may sound, all of this has been improved significantly. This new work is called Agent 57, and it plays better than humans on all 57 Atari games. Absolutely.
So you can see how the field is really progressing, how new ideas are constantly being developed, and we're heading in new directions where the new state of the art is surpassing human level performance across an entire benchmark of data. So Let's have a look at one more
Hold on to
example.
your papers, because this work on AlphaGo is absolute insanity. In the game of Go, the players put stones on a table where the objective is to surround more territory than the opponent. This is a beautiful game that is particularly interesting for AI research because the space of possible moves is vastly larger than in chess, which means that using any sort of exhaustive search is out of question, and we have to resort to smart algorithms that are able to identify a small number of strong moves within this stupendously large search space. The first incarnation of DeepMind's Go AI, AlphaGo, uses a combination of a policy network that is responsible for predicting the moves and a value network that predicts the winner of the game after it plays it to the end against itself. These are both deep neural networks, and they are then combined with a technique called Monte Carlo tree search to be able to narrow down the search in this large search space. This algorithm started out with a bootstrap process where it was shown thousands of games that were used to learn the basics of Go. Based on this, it is clear that such an algorithm can learn to be as good as formidable human players. But the big question was, how could it possibly become even better than the professionals that it has observed?
I'm going to skip some of the details there and just move ahead to this chart here.
Access to any human played games in the first phase and learns completely through self-play. It starts out from absolutely nothing, with just a knowledge of the rules of the game. It was trained for 40 days, and by day 3, it reached the level of AlphaGo Lee. This is above world champion level. Around day 29, it hits the level of AlphaGo Master, which is practically unbeatable to all human beings. And get this, at 40 days, this version surpasses all previous AlphaGo versions and defeats the previously published world beater version 100-0.
So again, this is another really nice idea where you basically have agents playing competitively against themselves, and over a long period of time they learn superior and more superior policies to exploit the environment to win the game and maximize the future reward. And lastly, this is one of the really remarkable areas of this field is the fact that the agents themselves learn behavior often in surprising ways. So I'll just let the video speak for itself.
Today, I am really excited to show you 4 experiments where AI researchers were baffled by the creativity and unexpected actions of their own creations. You better hold on to your papers. In the first experiment, robots were asked to walk around while minimizing the amount of foot contact with the ground. Much to the scientists' surprise, the robots answered that this can be done with 0% contact, meaning that they never ever touch the ground with the feet. The scientists wondered how that is even possible and pulled up the video of the proof. This proof showed a robot flipping over and walking using its elbows. Talk about thinking outside the box. Wow! A different robot arm experiment also came to a surprising conclusion. At first, the robot arm had to use its grippers to grab a cube, which it successfully learned to perform. However, in a later experiment, the gripper was crippled, making the robot unable to open its fingers. Scientists expected a pathetic video with the robot trying to push the box around and always failing to pick up the cube. Instead, they have found this. You see it right. Instead of using the fingers, the robot finds the perfect angle to smash the hand against the box to force the gripper to open and pick up the box. That is some serious dedication to solving the task at hand. Bravo!
So you can see more examples like that. But the fact is that we can often set up our rewards in such a way and set up our agent and just leave it running, leave it exploring. And often the solution it finds is the one which maximizes the reward. It might be something that we as humans can't even imagine how it could do that. So that's one of the really exciting areas of this field, reinforcement learning, is the fact that we can often be surprised by the outcomes. You often don't really get that in, say, other deep learning applications or even just general applications in computer science, because normally as we code, we kind of build up some expectation of what's going to happen, which we're less surprised by. So how does reinforcement learning actually compare to traditional machine learning? Well, we've sort of touched at it already, but with traditional machine learning, generally you have kind of either supervised learning or unsupervised learning. In the case of supervised learning, you have this supervisory signal. So you have this idea of immediate feedback. Let's say you're training a classifier. You already have the annotations of the data, so you can get your prediction from your network, and then immediately you can see, do the predictions match the annotations? And you can compute some error, and you can backpropagate through and adjust all your parameters according to that immediate feedback. And even in the case of unsupervised learning, usually you have some kind of model or some metric, some measure that you're minimizing, or if you're learning a distribution over the data, you have some prior information and you're trying to minimize, again, some metric or some measure over the space. So there's this kind of immediate feedback involved. Also with machine learning, you have IID, or independent and identically distributed data sets. So this is where you collect some data set and you train on the model, but you expect that when you test it, the testing conditions are going to be similar to those training conditions. Now in reinforcement learning, we don't have IID data sets. Actually, the data sets are dynamic. The distribution, you can think of it as always evolving, always changing. So if you're learning to drive around in an environment, maybe it's sunny and then later it's raining and snowing. Everything's always changing. Maybe there's like unexpected things happen that you've never seen before. Maybe like a pedestrian just jumps out in front of you. The other main difference, I suppose, is that the notation of reward, we don't have this immediate feedback. Instead, we have sparse or delayed rewards. And we actually try to gain rewards or maximize our rewards in the future. So this is very interesting because it means that sometimes the optimal behavior is to kind of sacrifice yourself now or immediately, such as to gain future rewards. So it might be that the optimal policy is to study really, really hard so that you can pass your exam in the future, even though it would be much nicer to sort of just go to the pub. So we don't have immediate feedback. We need to somehow plan ahead and work out what the best actions to take now are, even if they are not necessarily the best ones for ourselves in the short term. So they're the kind of main differences. Now let's sort of look at a very brief history of this field, where it's all come from, what the early ages were and way of thinking was. And I recommend you click this link here if you want a more comprehensive history, and that's given by Professor Barto. But it's quite long, so I'll just kind of condense the key parts of it here. So if we go way, way back to sort of 1874 to 1949, there was someone called Edward Thorndike, and he had these interesting psychology experiments. He was a psychologist, where he designed these puzzle boxes, which were these fun little contraptions, and he would put cats inside them. And there were different mechanisms that the cats had to figure out to escape the puzzle box. And he designed various different ones. So what would happen was the cats would basically just wander around almost randomly within the puzzle box, and eventually, over enough time, they would accidentally stumble upon the mechanism. They would see that it would make the door start to open, and then they would adapt their policy to be more interested in that mechanism, and then they would figure out how to actually exploit it and leave the puzzle box to get their reward. And by studying this after multiple trials, he coined the term law of effect in 1911. And this is that if you do something followed by some satisfaction, then you're more probable to do it again. Whereas if you do something that's kind of discomforting, then you're less probable to do it again. So if you recall the Hebbian theory of learning that we looked at in deep learning, you'll see there's some kind of similarities here, where if we have some context, we strengthen our pathways within that context within a short period of time, so that we sort of, if there's something we're enjoying, maybe we're making lots of new pathways in our mind, so we're going to repeatedly do those actions. You might sort of recall how synapses work, synaptic plasticity, and so on. So originally this was called learning by trial and error. However, I think it's better to sort of think of it as, rather than thinking of the idea of error correction, it's maybe better to think of like evaluation or trial and evaluation, this idea of evaluating behaviors. So this kind of way of thinking is often sort of linked to what's called behavioralism, is a behaviorist perspective of learning. That's a little bit controversial in today's psychology, just because we have a much more large and complete picture of learning now, which includes things like group dynamics and so on. But it's still useful to sort of understand the foundations, the basic principles, which there are some underlying similarities, which is that we have an environment, we generally memorize and make connections to what works well in that environment and repeatedly do those connections. And then we move forward a little bit more in time to the problem of control, which is where we're not just learning to sort of plan our way through an environment, but we're also learning to control or have some agency over it. So here's where you can imagine putting yourself in like a complex factory or a factory-like environment where the actions you take actually determine the outcome of what happens next in the factory. So we have to be very careful with what actions we take because we can have devastating effects later on. So there's this kind of field of optimal control theory, the problem of designing a controller or an agent to minimize the measure of a dynamical system's behavior over time. And one of the real main advances in this field was something called dynamic programming, and one of the main people in this was Richard Bellman. And really, as a kind of very simple overview, dynamic programming is where you kind of have lots of states in your environment and you expand like a tree out for all of those states. So if you're playing a game of chess, you've got a load of different actions you could take. You can move the pawns or the bishops, the queens in certain positions. So you've got like this state space of actions you could take at any one point in the game. And with dynamic programming, it's really just a way of solving or finding the optimal path through this state space, just using common sense. So you kind of do like a breadth first search, and then you go down deeper in the tree just with some sensible decision-making process. So you don't just like naively explore all of the states, which would often be computationally intractable. The problem with dynamic programming, however, is that it suffers from the curse of dimensionality. So let's just think of like the branching factor of Go. Go is much larger than chess. There are many, many more moves you could take in a game of Go. So it's got this huge branching factor. And if you were to just naively try and explore every possible state, there's just no way you can do it with today's computation. So there was this really nice idea that came out of, came from Richard Bellman, called the Bellman equation. And the Bellman equation allows us, if we've got some sort of constraints, to break down the problem into a more localized view of the environment. And we'll come on to this more in the next lecture, and we'll look at what the Bellman expectation and the Bellman optimality equations are. But they're really foundational to this field. They allow us to basically break down a large search problem into smaller sub-problems which are optimal at every smaller step, such that we can then solve the larger problem as a whole, just in terms of smaller computational stages. So this is a classic example, this cart pole balancing problem, where you've got this kind of process where you want to keep the pole upright, but you're only allowed to move left and right horizontally on the x-axis. So your agent can only move left and right, and you have to balance this pole. And actually, you can have lots and lots of poles all on top of each other, and so it becomes a more difficult control problem to make them all stay upright. You've got to sort of edge and follow all more complex dynamic behavior over the time, and it corresponds to where the pole's currently at, the angles, and so on. That's kind of classical control problem. And then if you just think to yourselves, well, what would be the most intuitive way to solve this massive tree branching problem with high branching factors? You might be thinking, maybe we could just randomly try some episodes or pathways through the state space and just learn a policy by, a bit like what we do in deep learning with stochastic gradient descent, just randomly stochastically trying out different paths and somehow trying to learn from all of our averaging over lots and lots of random trials. And that's really going into Monte Carlo tree search and Monte Carlo methods in reinforcement learning. So, I mean, classically, reinforcement learning has this reputation of being very, very slow. because the state space grows exponentially with larger and larger branching factors. So for example, with just 10 to the 20 states, which actually isn't that many in some games, just one sweep of dynamic programming would take thousands and thousands of years. But with Monte Carlo methods, we basically just sample randomly games, and we average our policies over those random samples. And we can now kind of explore these large state spaces with just sort of several million games. And in terms of reinforcement learning, that's actually really fast. So Monte Carlo is this idea of random sampling and averaging, so we can learn sort of expectations over lots of trials. Okay, so yeah, you can have a look at the reference there if you're interested in how it was used in AlphaGo 0. And that moves us on to temporal difference learning, which many researchers regard as one of the sort of main advances in reinforcement learning. So this goes way, way back. This is an image here of Gerald Tesaro, and he's actually showing way back in 1992 a multi-layer or deep neural network playing competitively with human experts using temporal difference learning. There's a remarkable paper which is actually using a phenomenal amount of modern techniques, just didn't receive much recognition at the time. And temporal difference learning is a bit difficult to explain just conceptually without sort of laying down the foundations, but I guess I can explain it just in terms of similarities it has with dopamine in the brain. So dopamine is one of the main neuromodulators in the brain, such as serotonin and histamine. And it's like this chemical, it affects these different targeted sites in the brain. The main function of dopamine relates to our pleasure and how we experience reward and pleasure within an environment. So specifically in neuroscience, dopamine functions as what's called a reward prediction error signal. And the phrase that really explains how it works is it's the degree to which the value of the reward is unexpected. So this idea of predicting what the reward's going to be at the next time step locally, dopamine is kind of like how much we're expecting that future reward, just that next stage along to be. So it's like we build this model of what we're expecting to receive, and then dopamine is controls the degree to which the value of that reward is unexpected. So it's kind of, you can see how it's maybe linked to the Bellman idea we just talked about, breaking down this long-term problem to this kind of prediction of the next step in the time step, and then how much are we expecting that reward. So this is modeled as what's called the temporal difference learning error, which was shown by Wolfram Schultz in the 90s by various experiments on monkeys. So basically the release of dopamine is based on the predictors of rewards. If you stop one of the predictors, then the monkey kind of anticipates the reward based on an earlier predictor. Okay, so if you kind of make some sound or have some flashing light, and then the monkey is expecting like to receive some treat or some snack if it sees the light, then if you suddenly get rid of that light, the monkey, but you still have the sound from earlier, the monkey's still going to be expecting the treat if he's heard the sound, because it's going back to a previous predictor. So there's this kind of backup process involved in temporal difference learning algorithms where we build a distribution over multiple predictors, and then even if some of those predictors fail, we still know what to expect in the future given previous predictors we've observed. That's kind of brings us about temporal difference algorithms. So they're like some of the main insights into reinforcement learning, the main kind of breakthroughs, and a lot of the state-of-the-art papers and methods you'll be using will be variants on Monte Carlo methods or temporal difference learning algorithms, but maybe using deep neural networks as well to approximate the expectations of predicting in the future, those kinds of ideas. So what are the sort of central concepts in reinforcement learning? Well, I think the most important concept is this notion of reward. And basically at each time step in an environment, there's some scalar or number, some floating point value signal, which is called the reward, our lowercase t. So it's just a real number. It just says what the reward is at that point in time. And the goal of the agent is to maximize the total reward it receives. And this means maximizing not just the immediate rewards, but the cumulative reward in the long run. And you might just want to think about amongst yourselves here, do you agree with this? Is this idea of reward sufficient? Can we really capture like all dynamic problems using this simple idea of having reward as a single floating point number? Is that sufficient? Is that enough? And I might just give some examples how it could be formulated this way. You don't need to agree. You might have other ideas, but here's just some examples. So let's say we have some game or some environment where the objective is to complete the game as fast as possible, like speedrunning. How would you formulate this as a reward problem? Well, what you could do is you could have -1 reward for every time step in the game. So the objective might be to just not have many time steps, because every time it does something, it's losing reward constantly. So therefore, what the agent's going to learn is a policy to just go as fast as it can to the goal, terminate, and then it's won with the minimal amount, as much reward as possible, which is because it's losing reward at a time, is to just go fast. So another example might be to have our reward defined in terms of the forward motion of a robot. So if you're wanting a robot to learn some graceful, elegant, fast way to run, then if you could just say it gets reward every time it moves along in the x-axis or in some axis, or the velocity of the robot. And therefore, as the process of maximizing this is going to involve learning a nice policy which helps the robot to elegantly move all of its joints to quickly move itself, the entire body of the robot, forward. Then there's the issue of sparse rewards. So for example, if you're playing a game of chess, you might be tempted to give yourself a reward every time you take an opponent or capture another piece, capture a pawn or capture a bishop. However, what's really important is that when we're playing chess, we only actually care about checkmate at the end. We only care about the winning conditions. So really, you should only design your reward such that you get some reward when you put the enemy or the opponent in checkmate. We don't care about the capturing all the other players. And this is important because if we were to give favor to immediate short-term captures, that might not actually lead to optimal behavior, to optimality. So the best winning strategy in chess is often to sacrifice some of your pieces or even major pieces such that you can achieve checkmate in the future. So designing rewards is really hard. There's a constant problem. It's easier to train if we have short-term rewards, like capturing players. The agents can start off by doing fairly sensible moves to, give themselves a good position, a good defense. But the really best policies to learn are where you have just the sparse rewards which really get you what you want. So you're constantly having to balance in the design problem. So this is a key challenge, as it's a challenge in many, many real world scenarios. If you've got kids, you have to constantly think, what motivation do I give to my kids to make them read and study and do well rather than just play video games all the time? Another nice example is from Greek mythology. You may have heard of the story of the Midas touch, where King Midas, he wanted everything he touches to turn to gold, but so he sort of designed this, what would be the reward here, surely that's a great thing to do, but didn't anticipate that he would only end up starving to death in turning his own daughter into gold by touching her. So it links into what we talked earlier about the idea of surprise, where we can often design rewards and not see what's going to happen. It doesn't meet our expectations. Okay. So the next key concept we're going to talk about is the action spaces. And what we mean here is that there are basically two main types of action agents can take. They can generally take actions from a discrete set of actions. So if you're playing a game of chess, you've only got a discrete set of actions you can take at any one point in time on the board. So you can only move your pawns into these positions, or your bishops into these positions, your queens into these positions, and so forth. So given a board, you've got a discrete set of actions. But in contrast, we also have continuous action spaces. So let's say your agent is a robot and your goal is to move as fast as possible. It might be that you can set the voltage levels of various components however you like in continuous space. So you can increase the voltages by some amount or decrease them by some amount. So you've got this entire spectrum of actions you could take, this distribution of actions you could take. So at every time step t, the agent sees something of the world. So maybe the agent has they have this observation. Maybe they have like a camera on the robot, or maybe if you're the agent and you're playing a game of poker, you've got your cards in front of you, then your observation contains your own cards, so you can see your hand. And then you have, at that point in time, you also have this notion of reward. A lot of the time you've just got zeros there because you don't know if you're in a good position or a bad position. But also, it could be like, how fast is the robot going, or has the robot crashed? That wouldn't be good, so we don't want any reward there. We probably want negative reward. It could be, once you've played the game, it could be your hand at the end of the game. So have you won or not? That could be your reward. And then we've got our actions there. So there's this idea of observability. So the agent interacts with the environment, and this is maybe a little bit controversial, but the environment itself gives the reward back and the observation back to the agent. But basically you can see there's this kind of outer loop over time where the agent is seeing things, and then it receives the reward from the environment, and it makes a decision, some action. It chooses to play a hand, or it chooses to increase the voltage of the component. It chooses to walk down the stairs rather than up the stairs to reach the pub. And you might kind of be looking at this and think, is this true? Is this right? And you'd be well within your rights to question this setup, but it's what we're going with in reinforcement learning. So, for example, do you agree that the environment should be what gives the reward? A lot of the reinforcement learning algorithms are formulated this way, where it's actually the environment which gives the reward back. So like the person in charge of the poker game might give you the money at the end. But similarly, you could think of scenarios, for example, imagine you've got this depressed agent versus this very excitable agent who sees beauty in everything. You might be then saying, well, surely it's the agent which determines its own reward. And in fact, there are models focused more that way. But this is the kind of standard setup we'll see in most of the environments out there, and most of the theory that you'll be encountering in papers, where it's the environment which returns the reward and spits out the observation. And because of this, we can actually say that the environment has a state. So what is a state? It's basically some values which make up everything that's happening in the environment. So consider your environment could be like some massive simulation. Then the state is like all of the parameters in that simulation that allow us to reconstruct the simulation at any point in time. And it's just really a formalism, but this is basically how we would notate the environment state. It's capital S to say that the states are at points in time, subscript T, and it's the environment state with an E there. So one of the first things we should say is that most of the environment state is useless to the agent's goals. So for example, consider a robot agent whose goal is to navigate a city. Then the robot doesn't really need to know what's happening inside the buildings. It doesn't need to know what people are having for their breakfast, but all of that data is in the environment state. So therefore it's good for the agents to actually maintain their own partially subjective state representation of the environment. And this leads us into the idea of full observability. So full observability is like the best case where the agent can see everything, all of the numbers that make up the environment. And the observation we see is the same as the agent state. So the observation is the same as the agent state, which is the same as the environment state in this case. And this all collapses into one state representation. And formally, what we call that is a Markov decision process. We'll come on to that a little bit later. But also, you have other reinforcement learning algorithms where you have partial observability. So you need a different formalism for this. We actually call it a partially observable Markov decision process, or a POMDP. And this is where the agent state is not equivalent to the environment state. So because of that, the agent needs to learn through, for example, using like a recurrent neural network or some function, it needs to learn the probability of where the agent thinks it is within the environment state. So we've talked about, well, we mentioned the word Markov. Let's just sort of break that down a little bit and say, what is the Markov property? What are Markov states? So Markov states are also called information states. And they're basically where if a state has the Markov property, you can throw away everything that came before it, and you can just keep your state. So how we would read this notation here, we would say the probability of the next state, or the state which is at the next point in time, conditional on the current state, is equal to the probability of the next state conditional on all previous states. And it might just be worth me putting this down on paper because there's many different abused notations and different notations people use. So if I just zoom my notes down here, switch over. Right, so I'll just rewrite this out. So we say the probability of the next state, t plus 1, conditional on the current state, is equal to the probability of the next state conditional on all previous states, so S1, S2, all the way up to ST. And in the literature, you'll often see different notations for probability. So one of the common ones you'll see is like a bold-face typeset T in square brackets. It's just really equivalent. Or we'll often see these kind of states here with the capital S represent random variables, but we'll often look at taking on a value of that random variable. So you might see some notation like this, where it's the same thing. This is just like an abused shorthand notation for saying the probability of the next state taking on the value of this state conditional on the current state taking on some value here. It's all kind of similar notation. Also, you might see lowercase p or a little p, probability of the next state conditional on some state. And normally in the literature we might use lowercase, well, it's kind of standard to use capital P for discrete random variables and lowercase for continuous variables, but often papers will just use the notation a little bit inconsistently. So long as they've defined it, that's okay beforehand. So moving down in this slide, we've said we've got this little bit of notation here, and what we're really saying here is that the distribution over actions and events for the entire future, so here's the entire future, so at some point in time going all the way into infinity, this distribution over events and actions is conditional only on the Markov state, ST, and that's the same as if we were conditional on the whole of history up to that point, so all of history up to that point in t. So they're all kind of equivalent, and that actually means we can, if we have this Markov property, we can throw away all of the history. In our simulation, we don't need to store all of the parameters for all of space and time up to that point in time. We can actually just throw away from that, all of that, and just be looking at our state if it's Markov. So that's very, very useful. And you might want to just sort of explore that within yourselves, think about it. So for example, here's a question: if you're like in a race with lots of cars, is just the positions alone enough to, is that Markov? Is the state of the car positions halfway through a race Markov? So I think the answer for that is no, because to approximate a Markov state, you would also need like the velocity information captured in the states. You would need the acceleration information captured in the states, and you would need the friction, the weather conditions, and the car weight. Only when you have all of that information can you actually sort of predict where things are going to end up to enforce the Markov property. And then you can throw away all of the history. If you don't have all of that data captured in the states, then you would need the full history. So we're now going to look at 3 important optional components to build agents, which are the policy, the agent's behavior, and the value, how good a state and or its actions are. So the policy is really just a function which determines the behavior of the agent, how the agent picks up its actions to achieve the most reward. So the policy is, an agent could be lazy, it could be really sort of energetic, and that how it behaves determines where it places its actions. And you get deterministic policies, which just determine how to map a given state to an action. So it's just any deterministic function which tells us how to get the most possible reward. So like in this noughts and crosses board here, in this state, and it's your turn, you should always play this action to win. But you can also get stochastic probabilities, which is the probability of taking a particular action conditioned on being in some state. So the probability of this action conditional on this state. So there's like some distribution over the actions we can sample from that distribution, and that helps us capture much more interesting dynamics. The value function predicts the expected future rewards, and this tells us how good or bad a state and action is. So how do I know if I should place an X here or an O here? To choose between them, we need to know how much total reward we expect to get in the future from taking that. And that's really what the value function is saying. So to read this equation here, we would say that the value of the state for a policy pi is the expected total future reward. And this is discounted by some factor gamma. Don't worry, we'll come on to this more in other subsequent lectures, but it's discounted by this factor gamma, which penalizes rewards which go further and further into the future. So this gamma basically allows us to say that immediate rewards are perhaps more important than long-term rewards, so we don't have to do so much computation and so on. And this is all conditional on being in some state. So notice it's for a given policy here. So a stupid agent behavior will probably have worse expected reward than, say, a smart poker player who's got this very good policy that he plays by. All right, and then our third main concept is the model. And the model itself just predicts what the next state will be and what the reward will be. So it's the dynamics of the environment. So those following David Silver's lectures, he splits the model definition into 2 parts. Sutton, in his second edition of the book, he models it as a joint distribution, which I think is slightly more representative. So I'm adopting sort of Sutton's ideas here because I think it's a bit more powerful. The environment's model of the next state and the reward are kind of interlinked with each other, so it's like a joint distribution. And in future deep learning lectures, we'll cover more about what joint distributions are and how we can apply them. But basically, you get 2 types of model. You get like model-based approaches, which is where you already have a complete model of the environment. For example, in some emulator for a video game, you can unwind states and you can see what happens. And therefore, you can actually solve those problems by planning. You plan through, in contrast to the actual full reinforcement learning. Planning is where you just expand your tree of states and you work out what your optimal path to play through the tree is. But then there's model-free based reinforcement learning algorithms, and this is really where the interesting stuff is. So it's possible to do all of the learning without building an explicit model of the environment. And instead here we can just go directly to the policy and or the value function. So we just observe and experience, and then we directly figure out the policy from our experiences or our observations. So that's really where a lot of the fun things are, where we don't need to build this massive model up. So just to kind of summarize, there are many, many ways to build reinforcement learning agents. And here's like a very coarse taxonomy, and it's somewhat useful, but in practice there's a lot of overlap between the fields. There's like this full spectrum of methods between the different algorithms out there. So a lot of this is about kind of deciding if the first thing you should do is decide, do I have a complete model of the environment or do I not? And then it's like deciding the components required based on how much exploration you think you need to do, how sparse the rewards are, how much you should be exploiting the environment, and so on. So next week we're going to be learning about Markov decision processes, which are like the foundational tools or building blocks that we use to express a lot of our more advanced techniques in terms of, and they're extendable to more powerful algorithms. So yeah, that really concludes this lecture. I hope it gives you something of an overview to the high-level components of reinforcement learning. If you want a more comprehensive overview, I would suggest you read Chapter 1 from Sutton and Bartow's book, but that's not really compulsory. If you have any questions so far, I recommend you come to our weekly Zoom discussions, and you can find more information about how to attend those from Duo. All right, well, that's it. I hope you have a good week.